Thanks for the invitation. It's very nice to be here. Now that I'm a East Coaster, it's nice to find out that all these schools are close by and there's great institutions in my neighborhood. So I'm very pleased to be here. Thank you. I'd like to talk to you about IceCube, which is an experiment, neutrino physics experiment that runs at the Earth's South Pole. So this is actually a picture of the South Pole, and this is a picture in the winter, which is night. So they're the same thing because the South Pole only has one day a year. So half the year it's dark like this, and in the winter the South Pole gets too dark for people to get in and out. Flights can't take off anymore. So what we do is we leave two people there by volunteering, who winter over basically and take care of our detector. And this is one of the pictures that our winter over took for us a couple of years ago. So this you see in the far background, a glow. This is like a 2-3-story building that houses our computers. Our actual experiment is buried underneath the ice here. And there's a huge question mark aurora on top of IceCube, which I think is very significant and sort of illuminating of the talk I'm about to give. So being trained as a particle physicist, I'd like to start with an energy argument. So here are the highest energy particles ever observed. And this is in our Earth's reference frame. So of course, you can tell me LHC collides very high energy things together, so the center of mass frame is different. But as me on Earth observing particles, here are the highest energy particles we've ever observed. So in terms of charged particles, LHC accelerates above 10 to the 12 eV, and then we've observed very high energy nuclei in the form of ultra high energy cosmic rays way out to 10 to the 20 eV. And in terms of neutral particles, gamma rays have been observed to about 10 to the 13 eV. And then in 2013, IceCube, and this is one of IceCube's events that I'll talk about later, saw this, a very high energy neutrino above a PeV. So the natural question to ask here, just by looking at the energy, is how are such high energy neutral particles created? Is there a connection between the charged nuclei that we see that's much higher in energy? The two neutral particles, can they have a connection? Could they be created the same way at the same place? And what is this neutrino? What is the most likely source? And where do they come from? What does it tell us? So here is kind of a general energy introduction to what I'm about to talk about, and also to remind you that I will use terms like TeV, PeV, and they're 10 to the 12, 10 to the 15 if you don't use them often, as I know it's very easy to forget. So here's my outline. I'd like to make a case for neutrino astrophysics first, then introduce you to the IceCube Neutrino Observatory, go through some results, and outline perspective for the future. So the case for neutrino astrophysics is really a case for multi-messenger astronomy. At the very high energy end, where we're interested in, you have cosmic rays, gamma rays, and neutrinos, as I said before. So the first question is, where do they come from? Supernova remnants, AGNs, gamma ray bursts, these are all hypothesized to create very high energy neutrinos, but we don't have definitive proof yet. The other question is, how do they get so high energy? What happens at the source is maybe another way to put it. And you can see that if you look at the same object and different sort of pairs of eyes, if you will, you see different things. So this is the Crab Nebula seen in X-ray, optical, infrared, radio, and then a gamma ray, which saw a flared state, and keeps seeing flared states. So what does this object look like in neutrinos? Would it look very different from any of these five? What would that tell us? So when you motivate neutrino astronomy, you show a diagram like this. And this is to say that here's a source way out there, and it's very powerful. It creates energetic particles. So if it created cosmic rays or charged nuclei, it would travel. But once you hit some sort of dust or clouds, it'll interact and deplete. So you see the beam getting smaller there. And then if there's magnetic fields in between us and the source, it'll deflect. So once we see it at Earth, it won't point back, and also it'll have depleted. And then the gamma rays, the same thing with the depletion, except for gamma rays, it does point straight back. So the usual argument is neutrinos point back, they don't deplete. Isn't that great? But I think it's a little bit more than that. So when we start looking at the charged particles, of course, high-energy cosmic rays that have been measured in many orders of magnitude of energy, when they hit something, when they hit gas or clouds, they go through a PP or PN type interaction. And of course, that means neutrinos get created. So the absorption of cosmic rays means creation of neutrinos. So really, where it got depleted here, there should be neutrinos coming out. Another thing about cosmic rays, like I said at the first slide, we have measured cosmic rays to extremely high energies. And if that is the case, and we all agree that there are CMB photons out there, they go through delta resonance and they decay into pions. And charged pions, of course, decay to neutrinos. So at very high energies, even if there is no clouds or gas obscuring the view, if you have a 10 to the 20 eV nuclei, and protons is the most effective way to do this, but any nuclei would do it, it'll run into CMB photons and create neutrinos. And these are called the GZK neutrinos. These are very high in energy. So there are dedicated neutrino searches, GZK neutrino searches. Experiments like ARA and ANITA you may have heard of is a detector fully dedicated to GZK neutrinos. Observatories like OJ and IceCube as well, we have dedicated analyses that look for very high energy neutrinos, which is kind of different from the bulk of the talk I'll talk about. But this is actually how I got my PhD, so I wanted to mention it. And as Aaron said, it was in the Bahamas. So it was a one-person particle physics experiment, which you've never heard of. And it was called SOUND, Study of Acoustic Ultra-High Energy Neutrino Detection. The reason why it was in the Bahamas, if you know your geology in geography, right next to the biggest island of Bahamas, it's called Andros Island, there is a huge trench underwater. So if you go out to a beach right here on Andros Island, it'll be shallow up to my knees or hip high, and then all of a sudden it'll drop 2 kilometers. It is like a Grand Canyon underwater. And why that's interesting, it's interesting because the US Navy finds it a good place to do testing because it's acoustically isolated and a nice environment to make sure that their torpedo warfare works, their submarines are quiet enough, things like that. So what they've done is laid down a massive array of underwater microphones called hydrophones. And what I did was when they weren't doing their work exercises, they would turn my detector on and I would acoustically look for very high energy neutrino showers. Very briefly, the way that works is the showers eventually convert all their energy to heat, and this happens fairly instantaneously compared to the speed of sound. So the column of water that was the shower would expand from the heat, and then the bath of the water would cool it back up, and that'll produce a transient bipolar pulse, and that's what I was looking for. So it is possible to do a one-person physics experiment, particle physics experiment. It is possible to get your PhD going to the Bahamas. But this is a different talk for a different time, obviously. So again, what I wanted to say was even when there is there's no target to interact with at very high energies, the CMB photons will turn the high energy cosmic rays into neutrinos, very high energy neutrinos. Gamma rays, which I will also briefly touch on here, there are 2 types of gamma ray telescopes, space-based and ground-based. They target different energies. They have different pointing capabilities. What I want to say here about in connection to neutrinos is that there are a couple ways to produce gamma rays, leptonic and hadronic. And leptonic can be like a inverse Compton scatter, so the electron, high energy photons upscatter a photon, which we seem to observe a lot. And then there's also another way to create very high energy gammas, and that is through neutral pion decay. But if there are neutral pions in some stellar or galactic environment, there should be charged pions too. So that will create neutrinos. So if we see gammas from neutral pion decays, maybe that is also a source of high energy neutrinos. So really, neutrino astronomy is more than just we can point back and it doesn't deplete. it has this intimate connection with cosmic rays and gamma rays at very high energies. Of course, what makes that great is also what makes it difficult to detect. So this is neutrino energy in eV, and here is the interaction length in a given medium. So if you are traveling through the critical density of the universe, a 10 to the 20 eV photon or 10 to the 21 eV photon is not enough. It will not be stopped in critical density traveling through the whole observable universe, which is about 10 to the 28 centimeters here. You go down to something denser like the atmosphere, then finally you're able to stop at the full vertical depth of the atmosphere, you're able to stop neutrinos. And I think yes. Oh, you're not able to stop neutrinos is the point. I'm sorry. It's not thick enough to stop neutrinos. And finally, if you're at the Earth's radius, you have a shot at stopping 10 to the 14-ish eV neutrinos. So what I said is, isn't it great? It doesn't interact with anything. It comes straight to us. Well, it doesn't interact with us either, is the point of this. So this is more of a detector problem, and I like this problem because, you know, as an experimental physicist, that means there's creativity in detectors that you can maybe do something about, and it's very easy to interpret once you see these neutrinos. At least that's my take. So here is where I break for a little show and tell. Here is how you get to the South Pole. If you've ever seen a globe upside down, Antarctica, of course, is a continent that's covered in ice. And what we do is we fly commercially to Christchurch, New Zealand, which is right here. And then from there, you get out of the airport. You go to a terminal next door, which is called the USAP terminal, or United States Antarctic Program. Here, you're issued all the gear you need to survive in the cold. So if you show up in shorts and a T-shirt, they will take care of you. And so here's my big parka. And then the first thing you do is to take a big cargo plane to McMurdo Base, which is on the coast of Antarctica. And McMurdo Base is really I would assume like a small town in Alaska. It's in Antarctica, but it's not like this permanently frigid place. You can actually see exposed dirt here. And that's the whole of McMurdo Station. That's the biggest station on the continent. And then from there, you take this small plane, and you fly to South Pole. And you go over these beautiful mountains called the Trans-Antarctic Mountains. Spectacular sight, very crammed inside your cargo plane. And then you land at South Pole Station. If you can see here, instead of using the wheels, it's actually on skis at this point, because the skiway at South Pole is not good enough for the wheels. And then you go to the South Pole marker, and you take a picture and send it home to your parents. That's what you do. So I want to talk about how big IceCube is. And we usually use this picture, which is kind of hard to tell because at the South Pole it's so flat, white, and desolate, there's really no reference points. But this is a 3-story building, huge building that houses all of computers and people, basically where we live. And then here's the skiway. Across from the skiway, this was the IceCube building that I showed you that houses our computers. And IceCube is buried under basically this patch of snow and ice. So looking at it sort of sideways, this is what it looks like. We have over 5,000 optical sensors, which we call DOMs, buried underneath the ice. They're instrumented between 1.5 kilometers to 2.5 kilometers in depth. And that's because the optical properties of the ice there is more favorable for Cherenkov light detection. What do we see when we let the detector run? Well, we see a lot of Cherenkov light. And neutrinos produce 2 types of signatures on a detector. One is what we call shower. So this would be all interactions, neutrino interactions, except for a charged muon interaction, charged current muon interaction. A particle shower happens, neutrino comes in, interacts in the middle of our detector, a shower happens. With the shower length is small compared to photon detector spacing. A lot of light comes out, but the light scatters a lot, so the optical properties of the ice down here are very clear but very scattery. So you see at the end of the day this big glow that comes out. And again, each each white dot here is one of those optical sensors. We have 5,000 of them distributed over kilometer by kilometer by kilometer. So this is a huge amount of light actually coming out. This is about half a kilometer wide. So you see from one neutrino particle, Cherenkov light, well, from one neutrino, you see a shower that's able to produce Cherenkov light over half a kilometer. So this is a... Yes, so this... Yes, so I'll talk about new-mu interactions next. That's right. Function of energy from muon neutrinos. How can we separate the flavors of the neutrinos at high energy? So, okay. So as long as we see a track, so maybe if I explain this slide. So when you actually produce a muon in the ice, then the muon just keeps going because of its mass, right? So it's a line, and so at very high energies, this muon is long-lived. So overlap of. So this is very clear, and the only time we can't really separate it is if it's not fully contained in the detector. So if the muon track sort of clips a corner, it's very hard to tell for us if that was a track going next to the detector that we saw light glow from, or there was a point here and there was a spherical emission of light. That's the only time we have a hard time separating. As long as the track or the shower vertex is inside the detector, we have no problem separating this. Excuse me?
What is the basic length of light in the ice?
I think, do I have, it is a couple hundred meters, I think. Yeah. So here's an interesting case where you actually see the interaction vertex of the nu-mu inside. So you see the hadronic shower around it, and then you see a muon coming out. So sometimes you're lucky you catch the vertex of the nu-mu interaction as well. But most of the times, because just from geometry arguments, because muons are long-lived and this can only be so big, you just catch the track that is the muon. Much smaller. Yes, and you will. Yeah, I think you will. I just wanted to say IceCube is a very big program, and we have a lot of areas where we contribute. I will only talk about really the astronomy that we do with IceCube, but I wanted to let you know that there are other things that I am by no means an expert to talk about. We are about 250 people, 40 institutions from around the world. Here's our diagram to show where we're from. And so I'm going to jump right into results. In 2013, we made the cover of Science because we discovered excess events at high energies using a veto technique. So what does that mean? So first of all, what is it excess to? The backgrounds, which we're dominated by backgrounds in IceCube, the backgrounds we see in IceCube come from atmospheric shower components. So when there's an atmospheric shower, it produces more muons than electrons and shower branches, which means that, but electrons don't travel all the way down, so we see muons as our primary background. This is in the southern sky, so the southern sky is down going for us. In the northern sky, we don't get muons because the Earth shields us from these muons. The next biggest background we have is nu-mus, atmospheric nu-mus. So these are not quite the neutrinos we're going for. We're going for neutrinos that came from outside our solar system, outside our galaxy, but these were just created by showers in the atmosphere. And then nu-es, of course. And in the northern hemisphere, you get these neutrino backgrounds too, atmospheric neutrino backgrounds too. Those overwhelm or trigger. Another thing about backgrounds, 2 more points. At higher energy, because the meson, the pion lifetime is longer, you don't have enough time to decay, so what happens is usually you just crash into the Earth and it interacts. And I'm sorry. And that means that these background spectra gets softer at higher energies. So it's going to be softer than the primaries from the cosmic rays. Another sort of caveat to this is that at very high energies, the shower is not full of pion and kaon, but more exotic mesons, and like exotic mesons like the charm lambda or something. And charm mesons, and these have shorter lifetimes. So these exotic mesons decay right away and have a harder spectra. But this is very subdominant. In terms of counts, it's low. So this is what's known as the prompt flux, and this you'll see is the background, a harder background for astrophysical neutrino searches. So here's everything put together. This is neutrino energies in GeV now, and this is flux multiplied by E squared. And what you see first is the falling down of the atmospheric spectrum. In black, those are the conventional neutrinos from the atmosphere. And then this is the prompt neutrinos that I just talked about. And again, the harder spectrum makes it a little bit harder for us to tell apart. And then hopefully astrophysical neutrinos at very high energies. So when we see an excess at high energies, we're excited because that's where we expect our signal to be. And in blue are the GZK neutrinos that I talked about earlier, which I will ignore for the rest of the talk. So how did all of a sudden did we see excesses at very high energies? So it was using a veto technique. And like I said, our primary background is atmospheric muons. Muons go through the detector and emit Cherenkov light as it goes. But if we define a veto region around the detector and say you can have absolutely no light in the veto region, your first interaction has to happen inside the detector, and then it can go out with light, you can cut down on the number of muons. So this has to be done with an energy cut, because at low energies, the muons can sneak in through between our optical sensors and mimic neutrino signals. So we impose the high energy cut, and we impose the veto cut. And after that, this is what we found. So here is our detected energy. Here's our event count. And the blue is the atmospheric neutrinos that we expect in count rate. Above that, so this is a stacked histogram, red or pink is still we get some muons sneaking in because they're so high in rate, 10 to the 6 times higher than neutrinos, that we just can't cut them all away. In some special cases, they sneak in. And then the actual signal we measured was in the black crosses, and you can see that there's excess compared to the background. This is combined upwards and downwards. Yes. So I think I have that in the backup slide. Maybe I can. Ask me again at the end, because I do have this nice picture that shows the zenith distribution of the events and how it matches expectations. For example, upcoming, you expect less neutrinos because of Earth absorption, and that happens more for higher energies, so you deplete the astrophysical neutrinos faster than the background. And it seems to match things like that.
How deep is the total
Is 1.5 kilometers deep in ice. Yes. Another thing about imposing a veto that we get is not only do we get rid of these these muon backgrounds from cosmic rays, we also get rid of actually neutrino backgrounds from showers, atmospheric showers. And the reason is because at very high energies, this whole shower, of course, is boosted, so it's very forward. And if we catch the neutrino, it's very likely they will get other shower components like the muon as well. And if the muon is also present in our detector, of course, it'll trip the veto. So by imposing a veto, not only are you getting rid of these muons that are our primary background, you actually also get rid of neutrinos, atmospheric neutrinos at very high energies. So this analysis, and that was updated actually in a PRL article last year with more data. The unfolding of this data can be shown here. This is neutrino energy in GeV again. I'm very sorry about the resolution of this plot. This is E square flux, and you see a little bit of downgoing trend, and indeed the best fit spectral index of the astrophysical component is e to the minus 2.3. The flux level is about 10 to the minus 8 in those units. And from the detector data, from this data, it seems like isotropy is consistent with isotropy, as in we see astrophysical neutrinos at the same levels from 4 pi. This is the latest data that we've published for the high energy stuff. This is the 2014 PRL. This is I'm gonna say like 50 TeV. Yeah. And I'll talk more about a low energy data set soon. So this analysis at least seems consistent with isotropy, and also the flavor ratio, because we can distinguish tracks from showers. We do see a consistency with 1:1:1 flavor ratio in our astrophysical neutrinos, which we expect if things are far away and not uniformly distributed, and neutrinos oscillate into an averaged out flavor ratio. Now, I'm sorry? So for this data set, it is consistent. However, since this one has, see, I have to be careful because it's roughly 40. I have to be careful because I know more data here, right, than we've published. So I'm subtracting in my head. I'm being recorded. We can talk privately offline, but while I'm recorded, the answer is 40. Yes. Well, so since we did this veto business, we've gone much more sophisticated. We're able to do a more sophisticated veto that scales on the energy and the direction it comes from. We parameterized our muon background much carefully, and the upshot of all of that was that we can lower the energy threshold, which means more statistics. Remember, any sort of falling power spectrum, the lower the energy, the more stuff you get, even though the background gets higher too. But if you can model the backgrounds, as these two technologies will let you, then you are still in a winning regime. So here is the updated analysis of that with lower energy data. Now the hemispheres are split into southern and northern to show you that the atmospheric muon contamination, red, only exists in the southern sky. Here's deposited energy in GeV, and I think the y-axis is just straightforward counts. Here is the energy threshold for the previous analysis. So basically, we had this on our hands, and then now we understand this much more. And of course, it's a log plot, so even though this is small, there's a lot more neutrinos in there than we previously had. The flux level seems to be consistent with the previous analysis, 10 to the minus 8, and those energies may be slightly higher. The spectral index, which this has the best hold on because you have more data in the low energies, so you can model your backgrounds as well as your signal better. The spectral index seems to be softer, minus 2.5, e to the minus 2.5. I don't think it does. I think they tried a couple of, I don't know what they used. I have to look it up. But they did try a couple of packages, and it made maybe 10% difference. So I can look up what the actual package that was used was in a minute. Sorry. I don't know that off the top of my head. So another thing is the data was fit to an astrophysical spectrum, this black solid line that was assumed to be isotropic in the north and south. And you can see with the data, there's a little bit of discrepancy. There's a deficit in the north and overfluctuation in the south. So it seems like there's some discrepancy once you look at the lower energy data. And this is extremely speculative because there's not enough statistics to say anything about it. But it seems like the flavor ratio is not exactly 1:1:1. And that's 1-to-1 is definitely within the errors, but it seems maybe possibly that it is muon neutrino rich. There, yes, it's possible there are backgrounds we are not taking into account. Yes, which would maybe try to explain the southern sky. Mm-hmm. Right. So first of all, it's very hard to explain this shape with these two lines. Right. So it's unless there's something, and then now you would bring up the prompt flux that had a harder spectrum. So prompt flux has theoretical models, but also limits from measurements. And if we allow for the maximum allowed prompt flux at 90% confidence interval, it actually doesn't affect this background spectrum much. So it's very hard to understand the excess and the possible not 1-to-1 ratio in terms of background, I think, unless we can come up with some different channels of backgrounds. I do not. And actually, this is not in the publication either. So I should probably take this off. But we could talk about it more offline. And then there's the third analysis, which is just looking at through-going muons, so through-going tracks in our detector. So if you limit yourself to through-going tracks that come up from the Earth, so from the northern hemisphere, if I'm standing at the South Pole, from the northern hemisphere up through my feet, then you know that it can't be muon background because muons can't go through the Earth. So you just have neutrinos in your sample, and here is the purple. I'm sorry, the green is the conventional neutrino background that you expect from atmosphere showers. Red is the, I'm sorry, no. Blue is, excuse me. Blue is the prompt flux that I talked about from maybe charm mesons. And then the data seems to deviate away, which fits an astrophysical prediction here pretty well. Again, the flux level seems to be consistent. It's 10 to the minus 8 at those energies. The spectral index, this is not a very high statistics sample, nor is it dedicated in high energy. So it has a big error bar, but it's about minus 2.2, which is consistent. Isotropy, you can't tell because this is just looking at one hemisphere. And I don't think the actual direction of these events have been unblinded. We follow blindness procedures in IceCube. And of course, this only looks at charge current muon neutrino interactions, so I cannot comment about the flavor ratio. So if you summarize the three analyses that I just went through, and understanding that one is completely a subset of the second, the overall picture seems to be that the flux levels, at least at 100 TeV, where these analyses are most sensitive, are consistent. Spectral index is softer than e to the minus 2. In fact, the second analysis excluded e to the minus 2 at a 90% confidence level. So it is definitely softer, but how soft is the question? There is some indication of anisotropy. It's unclear if that is an all-energy phenomenon or a low-energy phenomenon. And the flavor ratio, it's hard to imagine not being 1-to-1-to-1. And then comes the question, well, if you want to do astronomy, can you spatially resolve these things instead of just looking at energy histograms? So we do try this, and in fact, this is actually what I do. So spatial cluster analyses. Let's first give you a sense of our reconstruction capabilities with IceCube and neutrinos. Our pointing accuracy, and I know this is a more astronomy crowd, so please don't laugh at us, for tracks is about 0.5 degrees in directional reconstruction. For these showers, it's 15 degrees. I mean, if you do a careful analysis of the waveform on each PMT, which is fairly computationally intensive, and try all directions, then you can actually get 15 degrees out of this. What's kind of interesting is for energy, it's the reverse situation. Because tracks leave the detector with carrying away energy, we don't have a very good handle on the energy, maybe a factor of 2. Whereas if these showers if they're fully contained inside our detector, we have about 10% energy resolution, we think. It's 10 nanoseconds resolution. I think it's sub 10 nanoseconds, but we claim 10 nanoseconds. It's just light deposition. Yeah. And then comparing it to Monte Carlo. Right, right. And that is a very good question, I think. And usually, right. So we do have things that flash inside the ice of known like laser power output. If it's unclear if that's a very good calibration mechanism. Right, and so this is a good question, and I often get this from particle physicists a lot, and so it's interesting that you bring it up, actually, in this audience. But I think that is a good question. So there is no way to actually absolutely calibrate our detector, right? In short of making a neutrino beam at the South Pole, which is, we have done the cost analysis. It doesn't work. I'm sorry? Yes, but it's a calibration based on a measurement of somebody else's experiment. But yes, which is good. Yes, so everything suggests that we're fine. Yes, 10 TeVs definitely. But we have ways to reduce background at 10 TeV. Particularly, you're just reducing muons basically at that point. So if you're happy to calibrate your detector with atmospheric neutrinos, we seem to be very consistent. Also, I mean, this is usually what I tell the particle physicists is this is not like the third digit measurement we're doing here, right? We're doing like a factor of 2 energy measurements. So you're off by 50%. You're still in the same bin in a lot of log-log plots. So we have to be off by a lot to make this not work, is the other thing I try to remind an audience. But let me move back to our pointing capabilities and our clustering analysis. So here are the events of I'm sorry, this is the PRL paper. The first analysis I showed you in the diffuse analysis, this is in galactic coordinates. The purple color scale is just a test statistic or significance of how clustered things are at that particular point in the sky, taking into account all the data. And we don't see actually a significant clustering. This is, you might think that, oh, you have a lot of showers clustered there, but when you have a 15-degree thing, chances are they do cluster pretty often. So the p-value for that in IceCube, our p-values are always the chances that a background fluctuation can produce that. So this p-value is, I think, over 10% now, and that says that 10% of the time a random ensemble of isotropic events will cause that sort of significant clustering. So no significant clustering. You can see the sort of the isotropic isotropy of the events, and you would start to guess that extragalactic components are very likely in this case. We do a search around the galactic plane. So here are the different width around the galactic plane that we test, how clustered they are. Here is the p-value. Again, the lower it is, the more significant it is. The lowest we get is about, I think, 1% pre-trial. Post-trial is about 10%. So again, no significant clustering. But really, our real limit to clustering comes not from these high-energy events that contain tracks and showers. It actually comes from just collecting very good quality through-going tracks, because those are the things that have the best pointing capability. And asking yourself, are there any clusters in the sky? So now I've switched to equatorial coordinates. I'm sorry. And so in order to answer that, we have this complicated likelihood, but the upshot of that is you just ask yourself how clustered is it in space, and also take into account the energy information. The higher energy an event, the more likely or less likely it is to be background. So you include that in your likelihood function, and you get some sort of test statistics out, and that becomes the new map. And we look at the hottest spots in the northern and southern hemisphere, and you can see that our p-values, again, are very consistent with random fluctuations. So having not seen any clustering or sources, you can set a limit on the flux level of neutrino sources in the sky. And this is assuming that it's point-like. Our declination, so I'm very sloppy with zenith and declination because they're the same at the South Pole. I don't think I could ever be on an astrophysical experiment where it's not. But so they are very highly probable to be atmospheric in origin. this one. Yes. So really here, it's about half-half. Yeah. Yes, that's what we predict. Yes. So again, here's our limit. This is straight down going for us in the southern at the South Pole. Here's the horizon. Here is straight up going. Here is E square flux. And our limit is terrible in the southern sky because of the muon contamination. It gets better around the horizon, and then Earth's absorption of the signal kicks in, so it gets worse again. So that's how you sort of look at this shape of the curve. Here is the measured actual signal, diffuse signal. This is from the upgoing muon, through-going track analysis. Here is the measured signal level. So in order to explain this discrepancy, because this is a limit, anything above it is not allowed, and this is a measurement. And the only thing different between them, well, for now, is how many points in the sky make up this diffuse level. We can already say that this is about a factor of 15 off from each other, so you must have at least 15 sources in the sky contributing to this level of flux. Otherwise, we would have seen it in our point source analysis. There are many ways around it, which I can discuss more. This is based on, it's actually not 40,000, no, it's a lot more, but yes, it's based on this. Yes. Yes. Yes, absolutely. Right, but the garbage should not cluster. So the strength here comes from the fact that what we're looking for is different from background in two ways. It clusters in the sky, and it has a high energy tail. And that's what goes into likelihood. And that is much better than actually looking at the handful of events that we know to be astrophysical, because okay, let me get, maybe I can, if I can get to my second to last slide, and you can ask me again if I didn't answer your question. Okay. Another thing we do is stacking analysis. So you can argue that all of our diffuse neutrinos come from blazars. And so we take all the blazars that Fermi saw, or maybe a subset of them, and these are the 862 blazars we stacked. And at our angular resolution, this is about 10% of the sky. So this is not quite, this is like, is this 10% of the sky more special than the other 90% of the sky kind of analysis. And when we do this, and here's a lot of numbers, but the upshot is for all blazars, which is the top row, if you assume that all blazars have equal emission of neutrinos, or if you have the blazars will have a neutrino emission that is scaled as the gamma emission measured, either way, we don't see a significant clustering in those 10% of the sky. Right. It is. It is. Everything. Yes. 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 Right. Right. So this is a I think this is a good debate. Is it close by sources that is giving us these neutrinos, or is is the selection criteria something else? Is it maybe that there are special blazars that it doesn't matter, they're much further away, that somehow contribute more to our diffuse measurement? And I think that's a good debate to have, and something we have inside IceCube all the time. What makes them special that they emit neutrinos that we can see? Is it really just distance? That's a good question, I think. Oh, that's a good question. I think if you do it right, if you do it in, yeah, because I know you can have different cross-correlation algorithms too, but I think in most cases. Thank you. Yeah. Yeah. That's a, yeah. Yeah. for the one special blazar. Right. Yes. This is okay. Yes. Yes. If you're yes. If you're used to signal, if you're used to being able to see the sky and see clusters, this is a very hard game we're playing here. We're just excited we even saw anything at this point that's not background. So this is where we are. Okay, so let me say two more things about this stacking analysis. So once also the distance question is kind of taken into account when you weight the blazars by the gamma measurements on Earth, right? Somehow they should correlate. So the limit in flux, again E square flux, to neutrinos from doing this analysis, if you assume equal weighting for all blazars, is in green, and then in red is if you assume a strength level that is proportional to the gamma rays that you measured. Now let's compare this with the diffuse flux that we have measurements for. So here is the level of the diffuse flux that we've measured in the previous analyses. And this is our limit, depending on what kind of weighting scheme you want to try. So at most, blazars cataloged by Fermi can contribute up to about 16% to the diffuse flux that we see. In other words, there's no way to explain this diffuse flux we see in neutrinos away with just saying that blazars make it. Again, there's caveats to this. I wanted to just briefly mention one thing. I won't get into the data sample, but we do have a sample of interesting starting tracks that go way low in energy. So for the purposes of finding clustering, we can tolerate background. We are not background limited. And that means we can lower our energy threshold and take in a lot of tracks that seem to be starting inside the detector, and with the knowledge that most of these will be muons sneaking in. And we can still do that. And when we do that, we set a stronger limit in the southern sky for point sources, but also we discover interesting events like this. And this is one single actual data point example. Here is the dust layer that Kota was mentioning. We don't see photons from there because there's some dusty ice there, probably volcanic activity a couple thousand years ago, more than a couple thousand years ago. But the points are that this event starts inside the detector, so it's actually starting fairly deep. It's not that it is one or two layers of our detector deep. It starts very deep. Yes, I'm so sorry. Yes, it's red is early, then yellow, then green, then blue. I'm very sorry to skip that. And the largeness of the blob is the amount of light we see. It points, so that's interesting for us. It deposits about 80 TeV inside the detector. And at that level of energy, if it was a muon sneaking in, we should have seen a lot more light here. So it is very unlikely to be an atmospheric muon. In fact, this is something we found in a 3-year sample. We don't expect more than 0.01% contamination of muons of this kind. But also, it's very unlikely to be an atmospheric neutrino because, again, 80 TeV neutrino comes from a shower that's fairly boosted. So the chances of us not seeing any other shower component here is very low. We only expect about 0.2% in this data set. So calculated a posteriori, this event is like a 2.8 sigma fluctuation above background, and the single event now becomes interesting. And this gets back to the point of what is an interesting point source? Is it just one event that's very unlikely to be a background that points, or is it a cluster of things? In other words, in the era of diffuse astrophysical neutrino flux, how does one resolve a source, which sort of becomes like this semi-philosophical question. So we saw that a single event can be interesting, but, and here's the but, a single astrophysical neutrino event, we know for sure that something out there made this astrophysical neutrino in this direction. That can be the start of a lot of clusters around that point, or it could just be added to this unresolved diffuse flux part. And maybe we will never resolve many of our neutrinos that we measure. And in fact, it's kind of tricky because unlike gamma rays, neutrinos don't really have a horizon. You can see neutrinos from very far away. They don't interact. So really, worst case scenario is that we will only see diffuse neutrinos, and the only isotropy we'll ever be able to find is that they trace some large-scale structure mesh, and that would be very bad for us. So that's kind of our sort of what keeps us up at night. So let me summarize quickly. We've seen astrophysical diffuse flux at the 10 to the minus 8 level in those units, and the energy spectrum is very likely softer than e to the minus 2. We don't see clustering around anything. We don't see correlation with sources that we know are producing high energy gammas. We do much more cross correlation or stacking analysis than just blazars. It's just we don't see any correlation. So that's not great. So here's the challenges of neutrino astronomy, is that we really only have two things in our astronomy catalog, which is the sun, which is a very close by star and emits lower energy neutrinos. This is an MEV neutrino map. And the other astronomical object we've ever measured in neutrinos in human history is supernova 1987A. But this was not directional, it was just timing. In a certain time, there was a surge of neutrinos that they measured and went back down, and that time seemed to coincide with other astronomers telling us that there was a supernova explosion. So those are it. So, but maybe our first source is just around the corner, who knows, right? So history is actually on our side. Let me remind you the history of gamma ray astronomy. It started in the 70s when there was rockets being launched, and you see diffuse celestial radiation in gamma rays. And then fast forward a decade later, you start resolving discrete sources, and now, you know, gamma ray is astronomy. I don't think anybody will debate you on that. In the case of X-rays, the analog is kind of more interesting because the first ever X-ray source to be detected was the sun, actually. And then you see the diffuse emission, and then you start resolving sources decades later. So maybe we're on this trajectory, and we're just kind of halfway there, and we'll be able to resolve sources. And instead of a conclusion slide, I'll leave you with this. We are looking to extend our array. We have a next generation IceCube being planned. This is one such design proposal. So the red is the existing volume of IceCube, and maybe we can instrument a larger volume of ice at the South Pole. So we do have tricks up our sleeve, and thank you very much for your attention.